All right. Hi, folks. Welcome back to Fusion 360. On today's video, we're just going to continue trying to optimize shapes. And we'll probably begin right now with some topology optimization. But what I want to teach you guys how to do today is generative design. And I'll speak more about what generative design is in a moment. But let's first take a look at this quick shape that I designed in here. So let's suppose that you have some sort of beam that has to go, through here horizontally, and yet there's 2 points, in this case these two cylinders, that must be connected one to the other one, and there's a force being exerted on the top one, and maybe the bottom one is fixed to the ground. There we go, my mouse is back. So you need a shape that more or less looks like this. And at the same time you need to optimize for the mass, as we've done before, because that saves money. And for that purpose we're going to use topology optimization initially to see how that looks like. For those of you, before we do that, for those of you that are not familiar with the Fusion 360 interface, if you go down here to the bottom left corner, you can drag this little arrow in there, and you can see more or less how everything is coming about. In here, it's just like a timestamp. This is super easy, similar to SolidWorks for those of you that are more familiar with that interface. But yeah, so hopefully you can get a shape like this. Maybe more videos in the future will come explaining how to use Fusion. And for the time being, we can go to simulation. And I got myself a little bit ahead of the game, because I was about to begin a quick topology optimization. As usual, I clicked on study up there, and I clicked on shape optimization, as we've done before. Let me just click again in there, even though I'll cancel this one. Alright, everything seems back. My computer just crashed for a moment. Anyways, I always had just clicked in there, but I'm gonna cancel this one because we don't really need that for now. So as usual, what I've done in here is I've chose in green. Those are gonna be my preserved regions because I still want to keep them once the simulation is done. Then using my constraints and loads, I made the bottom surface of the cylinder. I did that fixed. This guy, I'm just applying a force. As usual, when it comes to shape optimization, let's see the criteria in here. Let's aim for 30% in here. Yeah, we got our preserved boundaries in there. Yeah, what else do we? Yeah, really. Yeah, we've done our mesh. Let me just do the mesh once more, just to be sure that everything is all right. Oh, let me just check. Yeah, it's this body. Let me just. No, I don't wanna. Setting. I might decrease that a little bit. Let me just click OK in there in a moment. Once my mouse is back again with power. There we go. Okay. Boom. Alright, folks. Turns out that my computer crashed, but I'm back again in here. So I just finished running this topology study in here, so let's close. And these are our results. So let's take a look at how this is looking like. So it kind of reduced the mass a lot, and yeah, let's see what else do we know. Yeah, the mass ratio is 32%. That is very interesting. The thing is that this doesn't work because it just eliminated all of this area over here. Let me see if I can increase that by a little bit. Oh, whether that would change anything. Actually, very interesting because it seems as if this is not connected at all. Maybe if we go back, yeah, let's finish results. Maybe if we consider this phase as one that we want to preserve, let's try preserving. Oh, well, no, that is. There we go. we're gonna leave it like that. Well, it doesn't matter if it's considering space, empty space as the one that we see there in the middle. Well, anyways, there isn't stuff that's happening in there, so it shouldn't be a problem. What I'm gonna do now is I'll probably make that radius a little bit bigger to 305. Maybe a tiny bit bigger. Yeah, why not? You know what? Maybe I'm gonna try doing the same thing on that one. Oh, interesting. I see. Well, I'm gonna leave it like that, and I'll rerun this study and let's see whether the results change. But like the point of this quick exercise is not to actually get something sensible out of this, because we're gonna do something better with the generative design in a moment. So let's solve this one study. Let's see. Give it a moment. Hopefully it will work. There's a chance it doesn't work. Well, my computer just crashed once more, and let's see whether this time we can make it work. So let's go back to optimization target. No, actually, yeah, let's edit this guy. And here, let's see whether we can aim for 60. Maybe I'm gonna increase the force in there. Maybe it's not large enough. Let's take a look at that lowercase. The load. And let's edit that, and maybe 100 is too little, so let's make it 1000 instead. And let's solve this study again. But the point again is, this is just to illustrate one way in which folks can optimize shapes given an existing geometry that you were given. For instance, this one in here. But I'm going to show you in a moment once this is done, and once we take a look at the precise results that this might give us, if it doesn't fail, about another way, which is generative design. I can tell you right now what it is. It's essentially taking inspiration from nature, and you just give it, you know, things that you want to connect. Let's say I got like 2 points, and I need to tell them, all right, these 2 points are subjected to these boundary conditions, and there's like this object that goes right in the middle. I'll show you in a moment how you can denote that, and you just tell the software, all right, connect those points, given all this information. All right, it did work. Good. Let's give it a moment. Well, interesting. This doesn't look good at all, but it's more or less what we would expect. Let's see, like these funky things. Let's just finish results, and I'm gonna go back to another tab, which is Generative 2 in here. So this is what I'm talking about right now. So I'm gonna go here to bodies to show you, and I'll hide all of them right now. So right now we got body 1, which is the exact same one that we had in generative number 1. It's the exact same thing. But what if I told you that instead of doing that, I just want these 2 cylinders, the ones that were the preserved regions on our previous design. We thought, all right, we got like this space in here that nothing can be in there. We got the space that is fixed, so there's nothing that can go in there. So then we tell the software, come up with a design such that you're connecting these 2 guys in the most efficient ways, minimizing mass and whatnot. So for instance, I can bring these guys. I just did them, I drew them in different bodies. So I can, there we go. So this is how it would end up looking like. So green denotes the areas that we are preserving, while red denotes the obstruction. Let's just change the colors. The reasons why I use these colors is because, well, those are the colors that the software uses. Because we can go back to here, generative design. So let's click in there. Boom, this is what it brought. Yeah, confirm. Again, we got unlimited credits, so it doesn't matter. We can use as many as we want since we are students. And then let's see, model components, bodies, and we want to hide body 1. So here we can see it. Even though the colors were just, they just disappeared, but it doesn't matter. So here's what we are going to do. You can also edit your body in here if you wanted to. I prefer to do it in the model area. That's okay as well. Let's wait until my mouse comes back. Well, it's not like so. In here, this is our preserved geometry. So I'm gonna click up there, and I'm gonna select that guy. Oh, 1 body and 2 bodies. I'm gonna click OK. Oh, so it turns green, the same green that we had before. And now for our obstacles or obstructions, these are the regions that we don't really want anything being designed in there. So I'm gonna choose that. I'm gonna choose that, and I'm gonna choose that. And then it has absolute freedom on how it's gonna connect those green bodies in there. Then design conditions. In order to do that, we have constraints, right? So I'm gonna hide body number 3 for a second, and body 4. There we go. Let's orbit for a moment. Oh, boom. Oh, where are we? Now, let me see if I can come back to my big mouse. I think this is, yeah, free orbit. There we go. Oh, where are we? Boom. I'm gonna, as usual, I'm gonna constrain that one, and then I'm gonna, for the load, let me hide the upper one. I'm gonna choose that guy, and let's apply 1,000 newtons. 1,000. There we go. Okay, gorgeous. And then design criteria. Let's look at objectives. So we can minimize mass, we can maximize stiffness, whichever we want, and we can specify a safety factor. I can say a safety factor of, yeah, I think 2.5. Again, recall that a safety factor is going to be the ratio between the yield stress, which is the stress of which this material, which in this case is steel, and we can also specify more materials than that one, over the design stress, which is the one that it would normally be operating at, given the design this is made of. So we can click there, OK. Manufacturing, this is super important. So with this piece, like what I love about Fusion is that you can tell it, all right, I want this to be done using a 3D printer. I want this to be done using a CNC mill, or it could be just unrestricted, right? We can do that. We can leave it just like that, as this is an example. Okay, but if you need to be more specific, feel free to do that. It's definitely gonna take a while. I've seen people telling me that it takes quite a long time for this to run. Regardless, then materials, study materials. Let's take a look at that. We can specify a couple of them, not just one. In this study, let's go to metal and choose aluminum. So we just drag it up there. What about steel? Let's use titanium. Why not? Yeah, let's do just those two. And let's do a quick pre-check. Yeah, so it would give you a warning, and this one goes that maybe this is too big to be 3D printed. Let's suppose one such 3D printer exists, so close, that is not a problem. I believe we got, I will say that we don't have a starting shape. Generally, this is very similar to what would be done in topology, but I'm gonna say not unassigned shape, gorgeous, objective, beautiful load case. So I believe, let's do a previewer. Let's see whether this is gonna tell us, right, more or less if we've done all of our, oh, you can change it. Yes. Or we can just generate. Warning, let's see the warning. Yeah, it's the same warning as before. So let's generate. And this might take a while. Let's see. Alright, folks. Well, it turns out that actually generative designs, given how complex they are, they actually take quite a while to run. So here's what I'm gonna do. I'm gonna continue covering more examples that I have up here, and then once the results begin popping up, I'll begin showing them. And it's gonna take about an hour or two, and of course I'm gonna omit all of that in the video. Let me go back to another design that I have before. I'm gonna just close that in there. Is that generative free? I'm not sure. Or maybe it is. Well, I think the main difference that I did here in Generative 3, it's literally the same design that I had in number 2, only that now I restricted, like there used to be a wall in here, and now it's all gone. And when before there wasn't this other wall constraining how big could this be. So in here I'm just restricting and providing more guidance to the software on the areas in which it can actually construct, in which it can join these two guys, right? So again, the beam or whatever it is that has to go between these two cylinders, it cannot, it has to go through this red area. That's why it's an obstacle. But then as for how we are actually connecting these green guys, it can either be through this channel that we are providing in there or through the outside. So this is another way, and we can go back again into design, generative design, and just run one more study using having this in mind. It's gonna run this study parallelly to the other one. So I'm gonna go back to model components, bodies. Again, that is our main body as usual. I'm gonna let's begin first providing. Oh yeah, we should actually first preserve our preserve regions are gonna be those two. And then let me show everything. Our obstacles are gonna be 1, 2, 3, and 4, just like that. Oh, use this mouse instead. Yeah, I got two mouses. The thing is that one of them doesn't work as well as the other one, but it's not of this computer. Then I'm gonna put the load in there. The 1000, good. Now I'm gonna do the same thing. I'm gonna put the fixed surface over here, and I'm gonna click OK. Let's show that guy once more. Boom. Let's orbit around. Oh, where am I? All right, give me one moment. There we go. Sometimes it does. Yeah, there we go. Free orbit. Sometimes it just changes. Anyways, this is what we got right now. Objectives, we can have the same safety factor, but I'm just curious to show you how would results change just by adding a few more obstacles, removing one, but like similar issues at the end of the day. Yes, we're gonna leave it like that. Materials, let's see whether we can add the same two that we had before. So that aluminium, and then this titanium variant up there. Boom. Let's see. Let's drag it up there. Oh no, I don't want incarnate. That is. This happened because my mouse just died while I was dragging. Let me just delete that one. Boom. Alright, close. Pre-check is gonna give us the same printed stuff. I don't want to previewer. I think we got everything, so we can generate one study. Yeah, we can save it there. So there in the loading area, we should have two studies instead of one. Let's see whether that is the case. It should begin appearing any moment. Oh, there we go. So we got one study. This is the one that we had already sent a few moments ago, and this is the new one that we are sending right now. How about it just completed one? Interesting. Finish explore. And then you can see this window appearing. Right now we're just gonna show us all of the different results that we're obtaining. Yeah, I'm gonna finish exploring for now. But we have one more design that I wanted to explore with you guys, something more useful. I'm gonna leave it here. And this is a chair. And I think this one will take the longest out of all of them. Again, we're still at the design area. This is not the generative design module. It's just that I colored it so that you guys can see with more clarity what is it that we want to do. But essentially, the green denotes all of the pieces that must be joined together. We've got an armrest, we've got the actual sitting space, something for the back, and of course 4 points where we're gonna connect the legs. And then in red, all of the areas that we don't want to include. And again, the more precise that we can be with these areas, the better, because the program will have just more information on what is it that we are asking it to do. We got in red in here that it's going to be the space which someone will sit. Then just below it as well, generate chairs to save space. We're going to obstruct all of that. And of course, we're indicating that this is on the ground. So in order to do this, the setup is going to be very similar, just we need to play a little bit more around with how we are establishing our forces. And I should say that we can have multiple load cases, but that again will take more computational time. So I'm just going to leave it like this. So we'll go to Generative Design. So we've got, again, recall all of these are different bodies. I'm just showing here, boom, we got a lot of bodies. Hopefully it shouldn't be too hard to design. It's just that every piece is different from the other one. So let's begin by our preserved geometry. So we're gonna select 1, 2, 3, 4, 5, 6, 7, and the extra chair. Yeah, let's just make sure that that is a chair. Yes. All right, we got 8 bodies, and then our obstacles will be 1, 2, 3, 4, and 5. We got those other 5 in there, so it looks just red and green as we had it earlier. Then our preserve. Oh no, yeah, that is okay. I'm just clicking here. Structural constraint. So what is it that it's going to be fixed? It's going to be those guys in the bottom. There we go. It was just that body. So we are gonna click that face. Oh, the face. Oh no, I don't want the edges. That's fit. And I did that fillet in there. It's like that face. There we go. But only just my mouse just died. So let's see. We got that 1 face, 2 faces, 3 faces, and 4 faces. Okay. Now, the actual forces, that's going to be a different story. And the reason for that is because... Right, so how much does a human normally weigh? There we go. I would say generally about 80. So like we can go for 1,500 newtons. That's gonna be pulling downwards. That might be a little bit too much. But again, this is what it would normally weigh, and then you could always have like boxes and whatnot, like a lot of weight. So yeah, that is okay. And then we're gonna continue adding more forces. In this case, I'm gonna eliminate that, and maybe in there we could have, I don't know, 500 newtons that direction. The more specific we can be, again, that is just better for the software, because it will have more information on how to design these chairs. Oh, and those spaces we can have again, maybe. As normally someone would, we can go for 500 newtons just to be completely sure of what we're doing. So, Right, that seems okay. All right. Let's see whether I can get my mouse back again. So we got forces in all those areas. Maybe the simulation won't end up. It's tricky, right? Because again, these are simulations, and it's hard to model what's gonna actually happen in the real world because folks don't generally use chairs. I mean, chairs are chairs, but many people give them other uses. So you need to account for additional forces that are gonna be applied. Then materials, we can add some aluminum as usual. I don't think titanium would make any sense. We could add steel. We can add definitely plastic. Let's see, we can find plastic. We got plastic. Let's add some ABS plastic. Let's add some, not acrylic. Yeah, I'm not sure what all of these fancy names mean, but like the colors on that side, they look good. No, not that one. Yeah, it's just this one. It's just called plastic. Leave it there. All right. Close. Let's see what is it gonna tell us. Maybe too large or free printed. I know that is okay. But let's just generate. I believe we got everything we need. Generate ones. Oh no! Before we do that, objectives. Let's give it a usual 2.5. And manufacturing methods. Yeah, it's gonna be unrestricted. Definitely not to the axis. It's gonna be milling. Maybe 5 axes would be better. Hit OK, and now, oh yes, generate. Generate one study. So let's see. So we got now this guy is gonna be sent. And so this is gonna be solved in the cloud, which again I do not know where exactly. Oh, it failed. Interesting. Alright folks, good morning. It's the next day since we began this video and results are in. When I posted earlier it's because I had to at the same time, so it was hard for it to process. But now everything is okay. I should mention though that I made a couple of modifications here. I extended this area up here, so I did a new body that is going to be body 14. Let's see whether, I need to escape this command real quick. So this box in there, just to avoid that area right above the armrest. And then I also extended this box upwards. That way it was clear the area where someone would be sitting down. Again, it shouldn't be too hard to design this geometry, but I can show you real quick how I've done that. If we go, I can go real quick to design in here. Actually, body 14, I modified it on there's a feature that allows you in Generative Design to modify all of your pieces. That's why you don't see it in here. But for instance, for this body over there, well, I can actually move the bar. Let's see whether I can reach that real quick. So it is that sketch in there. So I did just sketch like that, and I extended it in both directions. Then as for, let's see, what is this guy? Yeah, the same thing for there. I just did a projection of that line up there in that plane, and then I extruded downwards. Let's continue. I'm not sure. The base. That's easy geometry. But let's go back to Generative Design and here, and the results are in. So that's what I'm excited to show you about. I'm gonna begin with the most exciting stuff, and then we'll go back to our initial examples. It took about 12 hours, I believe. It was a long process, very long process, and here they are. And it is. I love classifying our results. First things first. Notice that a couple of them say completed, while a couple of them, they just disappear. They say converged. The difference is that when it says converged, it has essentially satisfied all of the boundary conditions and all of the requirements that we have imposed in our designs. While when it says completed, it's just that, well, the system is done performing the simulation, but it hasn't necessarily satisfied all of the requirements that we have imposed in here. Well, I just clicked in one, so let's take a look at it more specifically. But I think it looks pretty cool. It's quite an organic design. Let's give it a moment until it loads. Well, alright, turns out that my computer keeps on crashing, but we're back where I wanted to be, which is the main explore window, if you want to call it, of the generative design feature. Shows you all of the different iterations it went through. Oh, it finished saving, thankfully, in the previous video I did. Shows you all of the previous iterations that it has done. Again, completed means that it hasn't satisfied, but at least it's done. And you see the designs look pretty interesting, kind of similar mostly. But I'm just surprised with the way the software just, you just tell them, all right, you want to preserve that space, that space, that space, and like those little four guys, then just connect everything given our boundary conditions. And of course, there's the failed outcomes in here, which is, of course, expected. There's many different ways of looking at these results. I believe we can take a look at the scatter plot. This is one of my favorite ones, and it's organizing everything given, for instance, the material type. Here you got the mass, and notice that, look, there's one that weighs 2,400 kilograms. That is a lot. You expect most of them to weigh very little. In fact, like even 200 kilos, that is a lot for a chair. But anyways, this is just, it's just an example. And yeah, like you can hover around them and you can see which one is each design. Well, we'll look at the specifics in a moment. Yeah, you can, for instance, manufacturing method. These are all additive manufacturing. That's why they look much better. While these guys, and I wanted to point them out afterwards, they're 5-axis milling. That's why you see that it's basically, some sort of like end mill craving, just going inside like a big block of whatever metal this is made out of. Well, that is also plastic, just carving everything. Let's see, processing status. Yeah, converge, and it's not surprising that the only ones that converge are the ones that were made of 5-axis milling. That they basically all look the same. I think what changes is the material they are made of. But other than that, it's all the same. And then boom, you got all of these different guys. So let's go back to the main Explorer view. Let's take a look at one of these guys real quick. First, a couple of things to mention on this tab. Well, you see the status, the actual material, then it's unrestricted, that's the orientation. Then it's 5-axis milling. Volume, well, it's hard to visualize what millimeter cubic means, but if it makes any sense, this weighs 240 kilos, which is a lot. But again, the minimum factor of safety of this guy is 33.89, which is a lot. And there's a minimum displacement of 0.12 millimeters, which is like nothing. But that's because this is basically like a solid piece of plastic. Let's orbit a little bit around. Let's take a look at this design. So it's nothing special. You see that this is, of course, this expected empty right there in the bottom, and that's because we told it to obstruct to avoid that area. Well, I just lost my mouse, but I can continue with the other one I got. You can kind of see some of the areas that we wanted to preserve. Like here's one of the armrests, here's like the back side of a piece. But yeah, like it just uses a lot of material. So we wouldn't go for this design really. But it's good to understand when to use 5-axis milling versus additive manufacturing, because some people might have at their disposal different manufacturing methods, and that constrains our design. While in contrast, we got more organic and beautiful design when we just use additive manufacturing. This is made of just regular plastic. The mass is much lower. It's still quite a lot, I would say. 50, wow, 50 kilos, it's a lot. Maximum stress is 12 megapascals, that seems reasonable. And like the factor of safety and the minimum factor of safety of this design is the same, 2.5, which we had established before. And then I guess the maximum displacement is 99.24. I guess that is kind of a little bit, is almost 10 centimeters. Also, we can move this bar in here, and that tells you how the design would have looked like when it was at iteration number 20. Yes, it looks reasonable. I remember seeing something like this before going to sleep yesterday, but I knew if I left it for a longer while, you see that it's much more optimized now. There we go, it has appeared. Or you can also do pan, zoom in. Let's just zoom around. It's an interesting design. I like, how it came up with like these patterns. Again, remember that we were putting some force in here, so it has to be withstood with like these two bars. Then you got, look at that. That is an interesting way of holding. Again, the more specific we could have been by saying, all right, you cannot build in certain areas, the more information we would have provided the software when optimizing. But I think it did a pretty good job. It avoided these areas. It looks very good. It looks like somewhere like reasonably good where someone would be able to sit. Let's take a look at other designs. Let's see this one. This one is pretty similar. It has 34 iterations instead. Weighs slightly less. Max displacement is much lower. The orientation is just on the positive Z direction. It's still additive manufacturing. So let's give it a moment until it ends up appearing. And again, if you like what you've seen in here, you can go and I believe it's, yes, you can click literally up there, right? And it's gonna take this design over to the workspace, to like the design place, which we can do. The thing is that it would normally consume from you 100 cloud credits. Thankfully, we got unlimited of those because we're students. But otherwise, just be worried. Recall that the simulation itself, it just takes 25, while actually exporting this, it's 100. And that's because, well, you're probably doing generative design because you want to save money and whatnot. So the cost would be ultimately worth it. Yeah, this one looks interesting. I like these, ripples or step design that you see up there. Again, all of this area has been nicely avoided. It looks pretty organic. I'm a little bit skeptical about this front area, how it's gonna withstand the force, but again, I trust the software. Even though when you take this to the, to the design modeler again, you can modify anything that you want. You can make that stronger if you feel you have to. Like the bottom, the back side of the legs, they look a lot more like a normal chair would have them. I like a lot this on the side. Oh, I don't know why it's, there we go. These designs, yeah, the back also looks reasonable. And it did like this sort of shell behind the chair. Again, the only regions that look okay, the ones that we designed, which is like the backrest, these arm rests, the chair itself, and these 4 tiny legs. Let's take a look at one last one. Maybe this one, which we haven't seen the design of. And they all kind of look very similar. It's just the material that changes here. You see this one is made out of stainless steel. So the mass is a lot bigger. Wow, we still have the same factor of safety. And we have a much bigger stress. Interesting. Wow. This doesn't look super optimized, I would say. It looks a little bit cleaner, again, because this is steel. Look at how this guy is being held. Just like just a tiny bar. Well, that is really the same on the back side. It's cleaner because, well, it needs less material just to hold it. But overall looks good. Again, if you want this, you can just export it over there. Or let me just zoom out a little bit. But again, it took about 12 hours to do this, which might be a lot or not a lot, depending on what you are prioritizing. But again, you're just leaving the whole software to determine for you the best shape, the best way of connecting all of these parts, such that it reduces the mass and it reduces the stress given some material. So it's very smart. It's smart designing at the end of the day. Yeah, so I'm gonna pause the video here. I'm gonna continue with the other pieces. Alright, one last thing I forgot to mention about this workspace that you can see in here is that it recommends you a couple of designs. I guess it just pre-selects them for you because it just determines that they're good. Yeah, that's another thing to have in mind. Again, let me just finish exploring in here. So I just click over there. And we can go over to Generative 3 and Generative 2, which were our original examples at the beginning. Hopefully this is clear. It's very easy, intuitive on how to make these designs. Now let's go to Generative number 2. As a reminder, let's take a look at how this looked like. Originally this one failed when I was trying to run this design, but then I fixed it. Because again, we are constraining that wall, which in Generative 3 we aren't, but we are leaving this to be completely free, which in Generative 3 we're not. And we have like, that is fixed. And I said earlier that I wasn't gonna use a starting shape, but then I realized it was maybe better to use, so I used the original body, the one that appears in Generative 1. The one we did the topology of at the beginning, because I thought that would, I think that saved me some trouble afterwards, and I think the results look pretty good. Let's go over to explore, see what it has come up with, and you see all of these guys converged. Well, these ones are completed, which means well, it hasn't satisfied our boundary conditions, but many of them have converged, which is good. That is a good sign. Let's take a look at a couple of the things in here. It's made out of aluminium. The orientation is unrestricted 5-axis milling, so you would be able to use a CNC milling machine to do this. Well, much less volume, of course, than our chair. Mass is 3 kilos. Well, that makes kind of sense. Very large stress, maybe due to the fact that the cross section in that space is very small. It has satisfied the minimum factor of safety, which is good, and it has a maximum displacement of 3 centimeters, which is a little bit, well, I guess that is enough, as long as it doesn't interfere, it doesn't jeopardize the piece that is going through there, which is the main purpose in here. So let's wait a moment or two until this finish loading. And we can explore a little bit more how this piece looks like. Alright folks, my computer crashed once more, but thankfully we are back to where we were right now. So now we can visualize our shape. Nothing really interesting about it, mostly that it kind of used the contour that we had earlier as a, as a guiding space in which it could optimize. It looks quite reasonable, I would say. At least it is a very specific guidance on where to actually build, where to actually generate our design. Now we can go into observing a couple more. Most of these are actually converged. So that is good in terms of design, because as I was mentioning earlier, that means that it has satisfied all of our boundary conditions, which is good. So all of these will do the job. Again, it wasn't a pretty complicated design anyways. Oh, there my mouse came back again. Beautiful. Yeah, so there isn't much to mention about this one. Oh, there we go. I'm back here again. It looks quite okay, quite thin, I would say. You can notice that it has been optimized. Let's take a look at it. It is very interesting how that looks like in there. Yeah, let's take a look at other designs. Let's see what else we got. These guys look mostly the same. Let's bring this one in for a moment. And I believe there's a couple of that are either processing or they are just completed, so they have been optimized fully. Wow. This is all aluminium, additive manufacturing, so we would need a 3D printer that would print metal, which is not readily available as those that do plastic, but it's still quite okay. Yeah, this one is completed, so let's take a look at this one in particular. Interesting. Yeah, that looks quite unoptimized. It kind of did like some sort of like channel in there. Wow. Well, that looks okay. Let's go to the design because I want to remind you real quick about how this model looked like. Remember that wall. So now we're going to go to generative number 3. Generative number 3 is different. We have like this additional wall. We remove that one in there. And as a consequence, look at the Explorer. This one actually didn't take that long to produce results. And the reason for that is very simple. And it is given by what we'll see in a moment. Folks, as you can see in here, these designs are super simple. And that's because we suppressed as well. So that is why this is just an example to show how important it is to provide as much information as you can to the system. Because if you don't assume that it's gonna understand like what's the intended purpose. That's why in the previous one we did include well and this one no. As you can see, well, these are all converged, but it's a super easy design. And it's just because it did a wall right there on the left side, as we can see in here. Nothing really special. Yeah, that it does support the weight because it has converged. It satisfies the boundary conditions. But notice that it only took 16 iterations, which is about twice, just half as much as the other ones needed. So it's just an interesting consideration about how you should bear all of these in mind. So, well, folks, thank you for hanging around until this stage. I hope you learned something useful, and I'll hope to see you all next time. Have a good one.